Good afternoon, everyone. My name is Madeline Graham, and this is Team Hybrid 7, presenting our concept for a regional hybrid turboprop aircraft.
Hey everyone, my name is Ira Rosner, and I'm just going to kind of talk about some of the big picture here behind this project. Obviously, one of the big current initiatives within the aviation industry is a focus on developing hybrid or electric aircraft to reduce emissions. This not only has a benefit of a greener environment, but a big benefit, one of the reasons for adoption, is that it is much lower cost. Reduced fuel consumption, reduced fuel costs for airlines. Also can lead to really a focus for a more regional turboprop aircraft, simply because these powertrains can be very applicable to these more regional style aircraft, which can help to fill a gap in an emerging market for these smaller aircraft, especially in countries like Europe and now growing in the United States as well.
Many groups have a stake in the regional aircraft market and Hybrid 7's brand. Here I have highlighted what is most important to each sector of our stakeholders and why it is the best idea to choose Hybrid 7 for your hybrid turboprop option. For our regional airline customers, we can promise reliability, marketability, and a reasonable cost. Hybrid 7 promises deliveries made on time, aircraft that airline customers are excited about and willing to get behind. For our shareholders, we understand that it's important to make money. That is why we invite employees to share in profit with us. We also know that our brand and mission need to stay strong. That is why hybrid is in our name. Hybrid is not just a name, but a promise to deliver a new type of aircraft to the commercial market. For our regulatory bodies, the US government, the FAA, and ICAO, safety is our #1 goal while we strive to meet our ethical goals of reducing emissions. For reducing emissions in a safe and effective manner, Hybrid 7 is the way to go. Our fourth stakeholder is the general public, full of travelers who invest their time, lives, and happiness into regional travel, from sports teams that are traveling to competition, to college kids returning home to visit their folks over the holidays, to vacationers traveling to a port town for a cruise. Our promise is that they need not worry about their individual contribution to humankind's carbon footprint. This is a new kind of airplane and an exciting new chapter in commercial aviation, a revitalization of the turboprop. Our aircraft's mission will serve markets spanning 500 nautical miles, with a reserve mission of another 500 nautical miles if substantial diversion is necessary. Interfaces with existing operations include gate services, catering, passenger loading, fueling, and battery charging. Our aircraft will function on all existing North American runways and taxiways. Type certificate holders will execute the necessary mandated maintenance and conduct flight operations, while FAA-approved repair stations will conduct repairs of components. Communications interfaces for the aircraft will include a very high-frequency band transmissions, as well as capability for satellite communications. Navigation will interface with airport glide scopes for landing procedures. Radio communication will be possible with ground at all times during flight. Airlines will be able to customize their aircraft with additional navigation and communication equipment through Hybrid 7's partner contractors if other services are desired.
So now we will dive into more of the details of the development of this system and look at the high-level requirements. And we'll start with the functional high-level requirements, which are just requirements that dictate how the system will fulfill its goals, its tasks for the user. And our main example of this is the system shall operate from lithium-ion batteries and be able to produce at least 200 kilowatts of power. Next, we have performance requirements, which it just speaks to the operating capabilities and reliability of the system. Example of this is the system shall have a power supply of at least 40 watts when not performing a flight. And next we have constraints. This is restrictions, limitations, requirements that are set forth by the developers And a good example of this for our system is the system shall include a thermal management system that adds no more than 50 kilograms to the total weight of the vehicle.
While there are no real commercial hybrid turboprops in current existence, there's a lot of effort being put into studying the concept by a lot of major companies. Boeing has developed their hybrid truss-based wing, which would really be compatible mainly with unducted fins like the CFM Rise. De Havilland and Bombardier have been investigating this as a concept. Safran has begun testing. A lot of Indian companies like Pratt and Whitney are actually looking at this. They're currently working with De Havilland to develop a Dash 8 conversion. Pipistrel, the DA36 E-Star have both been test articles using hybrid or electric powertrains. So a lot of work has been put into it. Obviously, there are some pretty big issues with the scaling of the technology, with the weight of the batteries, so that have prevented it from becoming more commonplace right now. And obviously, there's a question of range, which is very critical with a commercial aircraft. The big functional requirements in play here, obviously the aircraft has to fly, it has to be able to, as a part of this, taxi, take off within 4,500 feet over a 50-foot obstacle, cruise for 1,000 nautical miles at full load at a minimum cruise speed of 275 knot true airspeed indicated, and land in, again, 4,500 speed over a 50-foot obstacle. For transportation, it must carry at minimum 50 passengers and crew accompanying them. It needs to be able to communicate both with air traffic control and over ADS-B. For navigation, it needs to both integrate modern avionics and also ideally have autonomous capability. Finally, the aircraft must be sustainable with a 20% reduction in fuel over a 500 nautical mile trip versus current turboprops. It needs to integrate well with existing infrastructure such as the wing size, baggage sizing, door placement, etc., etc. And materials and production techniques must be fairly common. There can't be anything too radical just so it doesn't become prohibitively expensive or take too long to manufacture. And then obviously it needs to be easy for ground crews to maintain.
Next, we have the morphological matrix for this system. And on this graphic, you can see all the different subsystems we have laid out with all of our different options that we considered, just so that we can make sure that we are selecting the correct options that fall best into our criteria of safety, environmentally conscious choices, and affordability. And we can see that with the main fuselage material being nano-adaptive hybrid fabric, which is highly resistive to flammability, and also using the biokerosene fuel as opposed to the more traditional Jet A fuel.
This N2 diagram showcases the proposed CNS avionics systems of the aircraft. This new aircraft will be able to make use of state-of-the-art technology to fly by rules. Autopilot will disallow stall-causing angles of attack or high bank angles, much like most of the modern aircraft we see in the skies today. Computers on board the aircraft will accept engine and air data and feed the information to the AutoFlight computer, which inputs controls to the various control surfaces of the aircraft. The aircraft's current position, engine status, heading, airspeed, and all relevant information is displayed on the flight deck, where the flight crew can monitor and make inputs. All inputs to trajectory made by the flight crew are fed through the AutoFlight system, which limits accelerations for maximum safety and comfort level for the passengers. The aircraft automatically transmits location, air data, and engine information to air traffic control and operators via transponders. Flight crew are able to communicate by voice via high-frequency radio transmission.
Now the big footnote of the requirements here, so we have our hybrid turboprop with its 20% reduction in fuel consumption over a 500 nautical mile journey. Some of the sub-requirements here, so the engine needs to be, sized as a function of performance requirements, but it needs to use an existing modified or future engine within a expectation for 2035 technology with a hybrid powertrain using a battery and alternator system. The cabin needs to be able to carry 50 passengers with a seat width of 17.2 inches, which is compliant with modern standards. It needs to have a similar layout to competitive aircraft with an 18-inch aisle and with sufficient baggage space for passengers. It needs to also be able to carry 2 pilots and 1 crew for every 50 passengers. The platform has to have a maximum wingspan of 36 meters that it will fit comfortably within modern airports. For performance, it must have a 1,000 nautical mile range at full load with a cruise speed of 275 knot true airspeed at minimum. an approach speed of 141 knots, and take off and land within that 4,500 window over a 50-foot obstacle. Finally, it needs to be able to be certifiable, capable of VFR and IRFR flight with an autopilot, capable of flight in icing conditions, and meet FAA 14 CFR Part 25.
Now that IRA has outlined our specific requirements, we can begin to conduct trade studies on potential technologies that could work to meet our requirements. Trade studies are important in systems engineering because they help engineers to make informed decisions about which design alternatives are the most suitable for a particular system. A trade study is a systematic analysis of different options, evaluating the advantages and disadvantages of each alternative against a set of criteria and constraints. This process is crucial for ensuring the final design meets the requirements, performs optimally, and is cost-effective. Trade studies provide several benefits in systems engineering, including that they identify the most promising design, they reduce risks, and balance competing priorities. For example, trade studies help engineers to balance competing priorities such as cost, performance, and safety to arrive at the best design alternative for a particular system. For our aircraft, the trade study we decided to perform was on airframe materials, and our objective with this trade study is to evaluate the suitability of different airframe materials for a new airplane design based on their performance against the specific criteria that were priorly mentioned by IRA. First, we will start with our criteria. The airframe material is an important factor to consider when designing an airplane for several reasons. First, the weight. The material used to construct the airframe has a direct impact on the weight of the aircraft. The heavier the airframe, the more fuel the airplane will need to carry or power it will need to produce, and the more difficult it will be to maneuver. Therefore, choosing a lightweight but durable material is crucial to optimize fuel efficiency and performance. Secondly, strength. The material must be strong enough to withstand the stresses and strains placed on it during flight, including turbulence, changes in temperature and pressure, and gust loads. The airframe must also be able to support the weight of the aircraft, the fuel, and the payload without bending or breaking. Third of all, the durability of the material is very important. The airframe material must be able to withstand repeated stress cycles and exposure to environmental factors such as rain, hail, temperature changes. It should also resist corrosion and damage from debris. Furthermore, maintenance. The material chosen for the airframe should be easy to inspect and maintain to ensure continued airworthiness. If maintenance is difficult or costly, it can impact the reliability and safety of the aircraft. Finally, cost. The cost of the material is an important consideration. Airframe materials can range in cost from relatively inexpensive to very expensive, and this can have a significant impact on the overall cost of the aircraft. Choosing a material that strikes a balance between cost, weight, strength, durability is critical to achieving a successful design. Some of the alternatives that were considered are aluminum, a lightweight, corrosion-resistant material that is commonly used in aircraft construction due to its strength and durability. Titanium, a stronger and more durable material than aluminum, but also more expensive. Another alternative considered were composites, both polymer and carbon-based. They're lightweight and strong materials made of a combination of fibers and resin, which can be molded into complex shapes. However, composites can be quite difficult to repair and difficult to maintain. Finally, an alternative was steel, strong and durable material, but very heavy, therefore making it much less fuel efficient. Ultimately, the technique selected for this trade study is the weighted decision matrix. This technique involves assigning weights to each criterion based on its relative importance and scoring each alternative against each criterion. The scores are then multiplied by their respective weights and added up to determine the overall sustainability of each alternative. Based on the criterion trade study technique, the preliminary decision is that composites are the most suitable airframe material for this airplane design. While composites may be more difficult to maintain, their lightweight, strength, and durability makes them a great choice for improving fuel efficiency and maneuverability while still supporting the weight of the aircraft and its payload. The cost of composites may be higher than aluminum or steel, but the overall balance of cost, weight, strength, durability, all of our criteria, make them the most suitable material for this design.
Finally, for the concept architecture, we're looking at a retrofit of an existing Dash 8 airframe. The wing and engines would be replaced for a much more modern, updated aesthetic and obviously performance, with new engines and a new wing for that efficiency. The avionics would be replaced for modern standards, the engines would be upgraded to a hybrid CFM Rise derivative, and the platform is already reasonably efficient, that new wing would maximize it and make sure that you could hit that reduction in fuel consumption. The highlight of this configuration is the CFM Rise engine that would be powering it. CFM is actually already looking at developing it into a hybrid powertrain, as you can see here from this engine, image that they provided. So obviously that's being worked on, and it is expected to be ready by 2035, so that meets the requirements there for the critical component, the engine. Obviously the big advantages here are how this would be a fairly low cost effort relative to developing an entirely new aircraft. You would simply be transitioning over to a new wing and a new engine that could be assembled as two parts and bolted onto the airframe in a similar mounting structure with the existing wing, saving on cost and retrofit time. Additionally, you would be able to minimize the amount of recertification work that you have to do, as the core of the airframe would be staying the same. New avionics, new engines, new wings, but it saves a lot of effort and a lot of cost and a lot of time there.